This is a very brief introduction to acids and bases, just meant to give you enough basic ideas surrounding some of the language that we can have you read about it and figure out some stuff on your own, give you some basic structure. So what you need to understand about acids and bases is it's the chemistry of water. We're going to be talking about hydrogen a lot, and we're going to be talking about hydroxide a lot, and it sort of stands to reason that, you know, hydrogen and hydroxide are what you get whenever water falls apart. So acids and bases are kind of really just the chemistry of water, and as water is the most important, like one of the most important chemicals to us on Earth, it dominates a whole lot of processes, so we need to understand it. So the basics of acids and bases are that hydrogen transfer is the key. So you have something that moves a hydrogen from one reagent to another. Acids are things that give away hydrogens, and bases are things that receive hydrogens. And this is the Bronsted-Lowry definition. Although you'll often not see the word hydrogen here, you'll see the word proton. And I just want to take a quick little diversion to prove to you that a hydrogen ion is actually a proton. If we consider the protons, neutrons, and electrons in hydrogen, clearly it has one proton. The average mass of the most common isotope of hydrogen is 1, which comes from the proton, which tells you that there are no neutrons in the average hydrogen atom. And since it's ionized, that one electron that it would normally have is not there. So a hydrogen ion and a proton are the same thing. So often we will, you'll see the Bronsted-Lowry definition will mention proton donors and proton acceptors. Bases are proton acceptors. And that's not different from hydrogen, it's just another way of saying hydrogen ion. We'll also see there are several other definitions. There's the Lewis definition and the Arrhenius definition, all of which have their moments, but I kind of think in terms of the Bronsted-Lowry definition the most often. So what do we mean when we talk about a proton transfer? So consider this acid. We know nitric acid. We're aware of it as being an acid. So what does that mean? Well, that means that when you put it into water, the hydrogen from the nitrate dissociates, breaks up, and goes onto the water, forming an ion. And you might ask, well, why does it do that? Well, let's take a quick little diversion. Remember our Lewis structure for water has these two lone pairs on this end, causing a net dipole, pretty strong dipole in that direction. And so the hydrogen from the nitrate, from nitric acid, will be so attracted to this dipole that it will leave and glob onto that. And so whenever hydrogen is placed into water and it ionizes it, that free proton never just kind of hangs out by itself. It will always stick to a water molecule, making this new ion that we haven't heard of before called hydronium. Hydronium is just a protonated water, meaning it has one extra hydrogen on it. So get used to that. Sometimes you'll see books or worksheets will use the hydronium description. Other times you'll see just a hydrogen plus one without the hydration shown, but you need to understand that those are equivalent. There's no real difference. It's just a difference in how they're being shown sometimes. So every acid-base interaction must have an acid and a base, because if you go back to our definition, acids give hydrogens away, bases receive or accept hydrogens. So you can't have an acid without a base. You can't give away unless someone takes. So who took this hydrogen? This hydrogen left the nitrate and went onto the water, forming a nitrate with no hydrogen and a water with an extra. So in this case, water is functioning as the base. So water, it seems, is a base. So there you go. And then a couple other definitions that you need to know. I want you to consider what these are. In the hypothetical world where this reaction would run backwards. It does not, but if it did, you see it runs forward only. I only drew a forward arrow. But if it were to run backwards, we could, if this process were undone, then you could actually talk about these two as having roles as acids and bases. And you can see that the hydronium actually, in the reverse reaction, gives its extra hydrogen away to nitrate for reforming the reactants. And so that is that's what would happen in the reverse. So this would function as an acid in the reverse reaction. So it gets a name. It's called a conjugate acid. And what received it? Well, this did. So this is the conjugate base. So whatever would receive or give protons in the hypothetical reverse reaction, we're going to call those conjugates. Now this reaction, these things are, I just got done saying that this only runs forward, so these guys are not very good at doing this. This conjugate base is weak. It's not very good at taking that hydrogen back. So this nitric acid, you'll see as we get through some other lectures, this is a strong acid, and what that means is it gives away and doesn't take them back. So it completely breaks up. All the nitric acid molecules will turn into hydronium and nitrate. So every strong acid has a weak conjugate. Strong acid, weak conjugate. So HNO3 is an acid, and its corresponding conjugate base is weak. Strong, weak. So let's do a different example. This, you can see I have double arrows shown here. That tells you that the reverse process is considerable. So what that tells you is that as this hydrogen fluoride, hydrofluoric acid, gives its HOA to the water, similar to last time, this fluoride being extremely, like the most electronegative element out there, this fluoride is very, very good at taking that hydrogen back and turning the reaction back into HF. So this is a reversible reaction. This is a weak acid. So hydrofluoric acid is a weak acid. And what that means is it's not very good at giving away its H and not taking it back. So what that tells you, this weak acid is its conjugate base. What does the reverse reaction is fluorine. That's our conjugate base. And we can see that it's strong. It's very good at taking that H back. So this is our definition of strong and weak. Strong acids run forward only and have weak conjugates. Weak acids run forward and backward and have considerably stronger conjugates. Now what about bases? So the most common bases are simply your alkali metal with a hydroxide. And if I put sodium hydroxide into water, it will dissociate, break up into sodium ion and hydroxide ion. Now you see there's not really we don't see a hydrogen being transferred here anyway. And this leads us to the Arrhenius definition of acids and bases. Different way to think of it is that acids dissolve in water to produce hydrogen ion, and that bases dissolve in water to produce hydroxide ion. So we can see that this, even though we don't see a transfer of hydrogen here, we see that it's breaking up, giving off hydroxides into the solution. This is a very strong base, and that indicates that it does break apart very easily. These do not come back together. So this would be our weak conjugate, and this would be a weak conjugate acid. So there's our strong base, there's our weak conjugate acid. There's more in the notes about some other specific strong and weak bases, but our final example here, this, you can see, if we look at this, we have ammonia, NH3, with water, and over here we have ammonium, which means that this is basically this with one extra H. it's gone from 3 H's to 4 H's. So this has received a proton to become ammonium, which means that this receives, if this accepted a proton, this is a base. Which, where did it get that H from? It got it from this water. So water is an acid in this scenario. Now, if you look earlier, we saw that water was a base. And in fact, water can function either as an acid or a base. It's amphoteric is the word describing a thing that can be either an acid or a base, depending on context. So you can see then if this is our base, this is our conjugate acid, meaning if you were to reverse the reaction, this would give its H away. And so that is our conjugate acid. And so our this is a weak base, and the way that you know it's a weak base is because we have our double arrow indicating that the reaction is reversible. It runs backwards as well as forward. So NH4 is actually pretty good at giving that H back away, which is our definition of being strong as acids go. So this is a fairly weak base, and this is a fairly strong conjugate acid. And since these are weak, they have these equilibrium reversibles, so we'll see that there are K's associated with this reaction. This is Kb for this reaction, and Ka would be what we would talk about for the earlier example of HF. And so you can look at those K values, and they work just like KSPs or K's equilibrium constants. They work all the same way, and so you could write out an equilibrium expression for this, which would ignore the water, of course. And so you know, for instance, that a thing is weak if it has a K at all. If you go look in a table list of Ks, you will not find HNO3 on the list anywhere because it's strong, and strong things don't have equilibrium constants because they're not reversible. So that's you know that it's weak if it has a K at all. And so that's a quick little introduction to some of the basics of acids and bases.